All right, let's do some antiderivatives. This is just a little bit of review. We're going to go back to section 5.1, antiderivative of x to the nth. X to the n plus 1 divided by n plus c plus the constant of integration. Don't forget that. Oh, yeah, n plus 1 on the bottom. Sorry. N plus 1 on the bottom and then plus c for the constant of integration. What's that rule called? Power rule. Part B, antiderivative of 1 over x dx. Close. ln absolute value of x. That's going to come into play in tomorrow's lesson. ln of x plus c. ln absolute value of x plus c. This hops over to the other side all the time. All right. Antiderivative of secant squared x dx. Tan x plus c, right? I was going to say tan x dx. It's not dx. Antiderivative of sine. Negative cos plus c. Antiderivative of cos. Sine. Okay? Why can we do those? We remember them. They're familiar to us. There's stuff on the board that helps us sometimes. There's a predictable set of antiderivatives that at this point you're expected to deal with, and those are some of them. It's not all of them, but that's some of them. This next page is not in your notes, but I want to give you the big picture. We need another tool in our toolbox because we're bored with the functions that look like that first page. We need to be able to anti-differentiate more complicated functions. So at this point, we can find antiderivatives if they fall into a nice category. Basic terms that can be written as ax to the n. We typically refer to these as polynomials. I think it also includes fraction exponents and negative exponents. Also can follow that power rule. Basic trig ones, exponentials, and 1 over x. Because they fall into predictable categories. We recognize them. We're comfortable with their derivatives, so then we can work backwards. The next thing we're about to do is kind of the chain rule answer for antiderivatives. Remember chain rule? Tootsie Pops? Differentiate the outside, leave the inside the same, and then differentiate the inside? Sort of. A little bit of recognition here. Today's our answer for that. What happens when you've got a composition of functions? Can you do the antiderivative? The answer is yes, and it is about u-substitution. Some indefinite integrals there for you to remind you. Some of them may be interesting later on. I want to go over a couple of examples. Okay. This is more complicated than what we've seen so far. We can't put it into one of those little categories. We can't turn this into a polynomial. You can't distribute the square root and make it the square root of 5 plus the square root of 2x cubed. You can't do that. You need some other sort of strategy. So we have to find a function that's familiar that also has a derivative inside this integrand. Okay? And here's what we're going to do. You're going to look for a function that has a derivative that's in there. Which function has a derivative that's also part of that? 2x cubed. Good. 2x cubed has a derivative that's also in there. Do you see it? There's a 2x cubed in there, and there's an x squared in there. Is it a perfect relationship? It's not perfect, but that derivative relationship is there. And what we're going to do is we're going to take that function that's inside another function whose derivative is also there, and we're going to call that u. So in this case, I'm actually going to make it just a little more complicated. I need to make it this way. It's not making it more complicated. But I'm going to have to call u 5 plus 2x cubed. Okay? Why? Because if I do the derivative with respect to x of this thing, remember that this d dx is an operator. If I do the derivative with respect to x, I get du dx is equal to 6x squared, right? Good so far? Is 6x squared in there? No, but x squared is. So we can mess with it a little bit. We're going to mess with it just a little bit. I'm going to take one more step on the du piece, and I'm going to say that du is equal to 6x squared dx. I'm just going to multiply both sides by dx. Algebraically, I think that makes sense. Good so far? Okay. What is that thing then? Using our new definition. What is that thing I underlined in blue? Square root of what? That's the square root of u, right? Good so far? So I'm going to write this as the square root of u times x squared dx. Now, based on the definition I created, which was not an illegal definition, I now have the square root of u times x squared dx. Our problem at this point is the u doesn't match the x. I need u times du. What's du? Du is 6x squared dx. Do I have 6x squared in there? Is 6x squared there? Could we make it there? We could, couldn't we? We're just going to completely mess with this thing. You ready to mess with it? I'm going to put a 6 here. Can I just do that? I can do that, provided that I divide by 6. But where should I divide by 6? Out here. It's one of those properties from yesterday, isn't it? Kind of messed up, but kind of okay, right? Mr. Best, you're way too excited about this. Yep. This is awesome. Did I change the integral? Not a bit. What am I going to do right now? I'm going to take this thing and put what in? Du. Because I've stated over here that that's du. I'm going to put it in. So now I need to find, I'm going to take one more step to make it a little bit easier. I'm going to write it as u to the 1/2 du. We have now taken a function that's weird, that we don't know how to antidifferentiate, and we've turned it into notation that we do know how to antidifferentiate. What's the antiderivative of u to the 1/2 du? U to the 3/2 divided by 3/2. In our mind, it's easier to write it as multiplied by 2/3 though, right? Then what? Good question. Where did the u to the 1/2 come from? This I defined as u, and it's underneath the square root. So here I wrote it as the square root of u, but the square root of u could also be written as u to the 1/2. It's a fraction exponent. Nope, du came from here. The square root of u went to this. This and this are the same. These two are married. And these two are the same. The x squared is gone because 6x squared times dx went in place, du went in place of it. This, I'm doing 2 substitutions, and that's why this is complicated. Thank you for asking the question. 5 plus 2x cubed, let's do it this way. 5 plus 2x cubed went in right here, which allowed me to do the square root of u. That make sense? Okay. 6x squared dx went in place of this. That's du. All the yellow things are the equivalent substitution. All the green things are also equivalent, but not the same as the yellow. Does that help a little bit? Okay. Just got to make it look pretty. We'll do at least one more example before we're all done. Okay. Okay. The only thing, I haven't done anything with the x squared yet. The only thing I did with the x squared is when I went to this first step right here, I moved the x squared over next to the dx. That's a good question. Should I back up? Would this be helpful? Let's back up. Okay. The first thing I did was once I identified u as the inside function, I'm now going to write, maybe this helps a little bit better. These are two separate pieces now. Those are the two pieces I'm going to care about. Okay? I said that u is equal to this, so now I'm going to write the square root of u, and then I have x squared dx. But I can't integrate u with respect to x. I need my variables to match. Okay? So now this is where I said that du was equal to 6x squared dx, and I want to be able to substitute that thing out and turn it into u's. Right? So now, if I can put a 6 on here, and a 1/6 out there, algebraically, I haven't changed the integral. Or arithmetically, I haven't either. Okay? So now at this point, this piece right here is equal to du. So I'm going to put du in its place. Is that okay? Okay. Now I'm going to integrate. This is going to be, what do we say, u to the 3/2 times 2/3 plus c. Got to bring it along. We done? Almost. Do we want our answer in terms of u? No. We want our answer in terms of x. What was u again? 5 plus 2x cubed. My answer is, I'm going to multiply these two. This is going to be 2 over 18, aka 1 over 9, times u to the 3/2. And u, we said, was 5 plus 2x cubed, plus c. Now, I don't know if I want to do it today, but just for fun, if you were to take the derivative of this, if you were to take the derivative of this thing, what would you get? Should we do it? We should. We should. How do I do it? How do I do the derivative? Exponent times coefficient, right? 3/2 times 1/9. That's 3 over 18, right? 1/6. 5 plus 2x cubed stays the same because of chain rule, right? Our exponent gets reduced by 1, and this becomes a 1/2, isn't it? And then what do I multiply by? The derivative of the inside, which is 6x squared. If I simplify that, look at the 6 and the 1/6, I end up with x squared times the square root of 5 plus 2x cubed. Does that look familiar? Okay. It does look familiar. It should look familiar. What is it? It's the function we started with. Okay? Let's do another one. This is not easy. That's why we're going to spend a couple of days on it. Let's get through example 2, and I'm not going to go to example 3 and example 4 because that opens up a whole new can of worms I want to get into tomorrow. Okay? What do we have going on here? Do you recognize anything here? Tangents? Where are you coming up with tangent? I heard tangent. What are you doing with tangent? What? Okay. Part of being really good at trigonometry is realizing when you can rewrite something in a different form. What's 1 over cosine squared the same as? Secant squared. So I'm going to, the first thing I'm going to do, I'm not even going to do calculus yet. I'm going to write this as secant squared 2x. Now, I'm going to do u-substitution. And the key to doing a u-substitution is identifying a function that's in there and its derivative is also in there. What's the derivative of, we don't know the derivative of secant squared, do we? Let's not go there. No, we know the antiderivative of secant squared. We don't, derivative of secant squared. A little complicated, isn't it? So what should we use for our u? Awesome. And let's differentiate both sides of that. What's the derivative? So I'm going to go du dx equals, what's the derivative of 2x? 2. So du is equal to 2 dx. let's rewrite this now. I have the antiderivative of secant squared u times dx, right? I did my first u sub. Good. Do I want plain old dx here? I want 2dx, don't I? If this was 2dx, I could put du in for it. So let's make it 2dx, shouldn't we? And you can only do this because it's a constant multiplier. If you're going to multiply by an x, don't do it, because it messes everything up. But if you can multiply the dx by a constant, do it. But if I multiply inside by 2, I got to multiply outside by 1/2, so I don't change the value. Okay. Good so far? Now I do my antiderivative. Actually, let's write this again. This is going to be 1/2 the integral secant squared u du. And I got to make sure the u matches, and that's my second substitution. Antiderivative of secant squared? Tan. So this is going to be tan u times 1/2 plus c. The 1/2 can go in, or the c can go inside or outside, doesn't matter. It's just the constant of integration. We done? No. We don't leave our answer in terms of u, because u don't matter. U doesn't matter. You don't matter. No, I can't say that. U doesn't answer our question. And that's, don't tell your English teacher I said that. U doesn't answer our question. What do we want? Your grammar radar is going nuts right now, isn't it? We want to substitute u back in. What is u? Tan 2x plus c. And you can put the 1/2 on the c or not on the c. It doesn't matter, because it's just a constant of integration. The 1/2 will take care of itself in the end. Okay? Those of you that like step-by-step stuff, if you want to put this on the back of your notes, the question, you might want to ask yourself 2 questions. When should we use u-substitution? You're going to think about using u-substitution whenever the function is more complicated than one of those familiar ones we recognize. A composition is involved is a big key. If there's a function composition and then a product of its derivative, you're going to want to use u-substitution. The derivative of the inside function also appears in the integral. How do you use it? You identify an inside function u. We're going to spend a couple of days on this, guys, because you have to practice a handful of these. Rewrite the integral with a u and a du in it, and integrate. Substitute u back in, because u isn't the answer. I'm not going to prove that for you today.